Rob is not sure whether he's a network-defined software engineer or a software-defined network engineer based on the things that he does. Over the last 2 decades, he's built networks and compute architectures and infrastructure for small application service providers, as well as delved deep into the architecture, design, and operation of IP infrastructures that support residential, business, and broadcast services and networks. Now he's focused on the evolving on and off device control and manipulation and management plane infrastructure, and doing some code hacking of his own, and leading the development of streaming telemetry, OpenConfig, and hybrid SDN systems within the wide area network for Google's worldwide network operations. He gave his first presentation to NANOG at NANOG 51 in Miami in February of 2011, and we are very happy to welcome him back again as a keynote speaker today. Please welcome Rob.
Thanks very much indeed, Steve. And it's a real pleasure to be back here. I think over 10 years since I first presented here, and that makes me feel old, but also over 10 years since we started on some of the journey that I'm going to talk about today, which is really taking a look back and looking at some of the lessons that I think we've learned building network automation over the last 10 years and beyond that. And really, I would say that it's exactly the right place to be presenting here, because I'm not here to market a particular solution, although the context of the talk I'm going to give is around OpenConfig and some of the lessons that we've learned there. I think there's really, these lessons are more about how we build these systems in operational networks. It's not about how adopting a particular product. It's not about taking a particular approach, but really just looking back and seeing how we might want to build things going forward, and whether we can take some lessons from the experiences that we've had thus far. And I'm going to start out just by saying, well, automation isn't new. You know, it's very trendy at the moment. There's a lot of new conferences, there's blog posts, there's different meetups that are happening. They're really talking about, oh, network automation. But I've been automating networks since the network is the one that's in the background of this slide, which is about 2003, 2004. And I wasn't the first one to do it. You know, we were automating networks back then by using Perl scripts or expect, and we were interacting with the only interfaces that we had available on those devices, which was the CLI. And this started us down a route of starting to encode some of the things that we were doing in scripts. You know, being able to take procedures that we were working through and building them into software, maybe so we didn't have to do them manually anymore. But I would argue that whilst that was where we started, and this is over, you know, almost 20 years ago, then we haven't actually evolved that far. The kind of state of the art hasn't necessarily changed. If we look at some of these blog posts, if we look at some of the tutorials that are out there, they're really still starting down this approach of writing scripts to achieve specific outcomes. And there may be some changes. You know, maybe we've changed from writing Perl to writing Python. Maybe we've started to be able to deal with some programmatic APIs that aren't just the CLI. Maybe we've even been able to adopt some vendor neutrality. But there hasn't necessarily been a step change in the way that we look at automation. And really, if you look at why that is, if you look at what we did, moving to these scripts, it was a necessary first step. You know, we needed to be able to move to scripting things because we wanted to be able to think about repeatability. We wanted to be able to do more operations. We also wanted to be able to think about how that would let us encode a clear process. We wouldn't have it that, well, this was configured on this network and I can tell because it's kind of that guy's or that engineer's configuration style. We got a way to be able to have a consistent process. We also got the ability of being able to repeatably run those things. We got the ability to make faster changes to the network. So we definitely needed that. And also it helped us start to move towards having safer changes. It started to have ways that we encoded the process, we encoded what we did, and as long as we got it right and tested it the first time, then we probably didn't have a mistake being made like we would if a human potentially was making it. But really this evolution is just thinking about faster typewriters. We essentially just took a way of doing some procedure to the network and made it faster. We didn't think about the way that we needed to react to the network's condition. We didn't necessarily think about how our scripts might need to, or our automation might need to have logic in it, to be able to say, this is the state of the network right now. What's a safe way to make a change? What's a reliable way to make a change? And I would argue that we have to move beyond just this approach where we're taking scripts and implementing them to make changes faster in the network. We rather have to look about building systems. And those systems have to be able to think about how we apply some of the network engineering common sense that we would have had in engineers ourselves into these systems, such that we can make the network evolve more quickly, we can meet the needs of our networks. And that's actually a question that I've debated with colleagues over the years. One of the debates that I've had is, do we really have to move towards network automation? Is this really a thing that is necessary for us to do? And one of the main reasons for that is not fear of technology. It's really about the simplicity of the system. If we start to introduce software that's involved in running our networks, then do we have the ability to reason about them and think about how they might fail in the same way that we would if we built them in a simpler manner, in where we'd had humans be able to understand exactly how they would work? And this is a good question to ask. Simplicity is an admirable trait to design into any system. But we have to think about what the business requirements of our networks are. If we look at the network today, it's critical infrastructure. We've changed the way that humans communicate with each other based on the way that internet communications and IP communications have opened up the new applications. And so we don't really have an option anymore not to address that fact. We've had to be able to keep scaling the bandwidth that's available on the network. We've had to meet these demands of new applications. But alongside that, we've also had to make the network go more places. We've had to expand its physical footprint as well as its bandwidth. So there's more network for us to operate. And equally, we've had to make it more reliable. Whilst long outages have never been something that are acceptable in our networks, they come under more scrutiny now when they happen. More regulatory examination, more interaction around why they'd happened. And increasingly, short outages aren't something that we can tolerate anymore either. So we don't just have to meet this scale requirement. We also have to meet these reliability requirements. And the only other option than go and augment humans with software here is to get more humans to do it. And we just simply can't grow the number of folks that we have available with that skill set at the right rate to be able to meet this requirement. And we can't necessarily ensure that we're able to make those changes safely either. If we're having to make faster changes, we need to figure out ways to be able to have software help those humans that are involved in the network, not make changes in a way that maybe deals with these bigger infrastructures that are harder or more difficult for us to get our heads around. So if we're thinking about building these systems, how could we evolve from this kind of scripting approach into this kind of system approach that lets us meet those requirements? Well, we could start out by just having multiple scripts that interact with the network. We could go and build different things that do different procedures, and that's kind of where we've been. But as the network becomes more dynamic, and we need to have different types of changes happen in the network, then that's not necessarily a sustainable position. A few years ago, my colleagues at Google presented a paper that enumerated the number of changes we made on our networks. And they looked at it they calculated it to be something around 30,000 changes per month. Now, Google's a fairly large infrastructure, but I would say it's become more dynamic than that. We didn't, at that point, have things where cloud customers could necessarily change things that directly impacted and resulted in a network change. So that number is probably a lowball estimate for today. And yet, Google's a large network infrastructure. But I've worked across a number of different industries, a number of different telcos as well. And I would say that I don't observe that it's a different pattern. So really, if we want to go and take all these different diverse operations, it's probably not sustainable for us to be able to build these scripts that do this. And especially it's not sustainable as we start to look at how to deal with the fact that the network is probably not the source of truth anymore. Before, we used to think about things and say, well, the thing we know is that the way that the network is configured is probably correct because that was the way the services were set up. But as we have more external to the network sources of truth, things like inventory databases, things like IP address management systems that are now involved, then yes, we can introduce these to our scripts. But we very quickly start to create lots of interfaces between different parts of the system. It becomes very difficult for us to reason about how the system's working. And it's not just that we need to get these tasks done for the first time. We need to get them continually done in a robust and a maintainable fashion. So really, this approach of creating a spider's web of different interactions, it doesn't let us do that. It doesn't let us figure out how to break down those tasks to test them. So I argue that for us to be able to build automation in a meaningful, robust, maintainable way, we're going to need to think about these kind of layered systems. We need to start to think about applying separation of concerns, having certain parts of the system that are responsible for certain tasks, and breaking that down, and having those have well-defined interfaces between them. So we might take something like on the right-hand side of this slide, and we might think about having a layer that works at an actions, a sort of workflow perspective, something like adding a peering connection. We might then have something that manages the topology and stores its inventory to do with the topology in that layer. And then a layer that deals with interacting with network devices. And this kind of system helps us break down functionality, and it helps us keep that maintainable and keep it robust. So to do this, to separate these layers, well, we need abstractions. We need something that is between those layers, and we need something that helps us not have all the details of every implementation at every layer. If we build this layered system, and we simply say, well, at the top layer, we have to know something like the vendor configuration language that we're going to use on the network device, we didn't actually simplify the problem. We need to be able to say, there's these layers of the system, and those layers have constrained functionality, and they have ways to interact with each other that doesn't involve all the information needing to pass through. And that means we need abstractions. And what do abstractions give us? Well, they give us a way, as I said, to constrain that complexity. They give us a way to be able to reason about a certain thing that a layer does, and then be able to take that and make sure that that is the implementation that it does. It also gives us a way to have reusable components of the system. If you think about things like safety checks or health checks in the system, we might have in our scripts, if we were implementing those individually, we might have many places where we need to go and enforce safety. And by safety, I mean things like, don't isolate this node, don't isolate this POP location. These kind of checks, if we create those solely in our scripts, then everyone has to remember to implement them. But if we implement in an abstracted layer, we can go and implement those things in layers that are reusable across different implementations, that make sure that we're making safe changes, that make sure that we're making the right changes to the network, enforcing our network design rules. On top of giving that reuse, we also get the advantage of being able to evolve things separately. If we expose all of the implementation details to every layer, then we can't just go and change an implementation underneath. A simple example here is if I wanted to be able to change the vendor on which I'm realizing some service, then if we've leaked that information all the way through the stack, it's no longer possible for us to go and change out the vendor. Equally, different software components might do the same thing. You might want to change out something like the topology management service. And if you've done that by exposing all the implementation details, it's impossible for you to change it without having to re-implement either that exact implementation or change all the systems around it. And the final thing that abstractions give us in this world is they give us very clear testing points. It's been traditionally very difficult for us to test network applications without having the actual network and building labs that are able to replicate that network. But we need to be able to evolve these systems in a way that meets new functionality, in a way that doesn't require us to have to run the thing in production to be able to see if it's correct. So having these abstract layers gives us points at which we can enforce testing. We can check that the output is what we expect it to be. We can check that the system reacts to the input in the right way. And that gives us really clear and firm rules for being able to change these systems as we build them. So I've kind of talked generically about the problem of network automation, why I think it's a requirement. But the context I want to talk about this is OpenConfig. And really, this comes from thinking about one of these layered systems. And so when we were originally talking about OpenConfig, we started to talk about not just, well, we need a device layer API. We started to think about how are we going to build systems in the future? How are we going to build automation systems in the future? How are we going to build networks in the future? And this was a cross-industry discussion amongst a number of us. And we really came to this vision that said, the only way that we're going to mutate the network in the future to meet the scale requirements, to meet the reliability requirements, is via machines. And machines are going to be the thing that mutates the network. And the machines need programmatic APIs. They need APIs that they can pass, that they can work with, that expose the right information. And this perception, this kind of vision of not just scripting, thinking wider about the wider way we build automation systems, then introduced some requirements into the technology that we built. We started to think about things like, well, if we're trying to build a system that can react to the changing in the network, if it can react to the way that the network looks, then we're going to need things like the way to examine the state of the network. We're going to need ways to be able to say, well, this is the state I expect the network to be in, and this is the state the network is in today, and to be able to anneal the two together. So that made us go and build fundamentally a different set of technologies than we would have done if we had not had this wider vision. And actually was one of the reasons that OpenConfig ended up splitting and diverging from other industry efforts like modeling in the IETF, was because we'd had this specific view. We also had this vision around abstractions in the stack. we said we needed to be able to port things between different implementations. We needed to be able to move these services around without having all details exposed through the stack. And so that meant we needed to abstract away some of the implementation details. And that's what led to this approach that this should be vendor neutral. We wanted to take something and say, well, it can't be tightly coupled to one implementation. It rather needs to be more abstract. It needs to be thinking about what we're trying to achieve and just include those details. And so this gave us the vendor neutral open source project that we formed around OpenConfig. And now it's 10 years later. We've been on this journey for 10 years. We've been building this software for 10 years. We've had this in hand from multiple vendors. We've built software systems that have implemented. I've built them at multiple companies. And so it seemed like a good time as the 10-year anniversary came around to think about, what have we learned? What could we take from this experience? And one thing I'm just going to say here, this is not me just standing up and saying, like, hey, here's all the lessons that Rob learned. It's actually, I've distilled from all of the efforts that gone in across the industry. It's hundreds of engineers across multiple companies. And so I want to try and distill some of that down. And I've been lucky enough to be in the position of being the tech lead for OpenConfig and a number of the things that it's done at Google for a number of years, as well as having been engaged from the start. And so I've been able to use that experience and see that kind of cross-project set of learnings that I would like to share today. So let's just level set, though. I'm talking about OpenConfig. I will just make sure that everybody's familiar with it and explain the journey that we went on. So to start with, what OpenConfig was a set of data models for config and telemetry. Essentially, we said we need some interface to network devices that exposes what the configuration parameters are, what the telemetry that's associated with them is. But very quickly, we realized that that's just not sufficient. To build these kind of systems, you couldn't just define these data models. You needed to think wider than that and think about how they're built into different systems. And so we moved on to thinking about the interfaces to network devices in terms of GNMI, which started to give us a way to be able to interact with those data models and expose them to the OSS systems for telemetry and configuration generation that we had. But if we take that holistic picture of what the device-level API, device-level abstraction needs to be in our automation systems, we said, well, it's not just that. There's also operations that we need to run. How do we interact with the applications that are running on a network device? Then we started to think, well, we also need to think about security. We need to think about, in this machine-to-machine world, how do we want to have enforcement of security? How do we want to have authorization, authentication, accounting of those things? And so we worked on GNSI. We then went further and thought about, well, we actually need to have these machines be able to turn up network devices from nothing. They need to be able to start at a blank slate and securely turn up a device into a manageable state. And we worked on bootz. We started also to blur the lines between the control and management plane and think about ways that we would do things that maybe could be management plane operations, but needed to be more dynamic, like route injection. And through this experience, the main clients of these systems are the OSS systems. But we also realized that we had another set of users. And that's really important because OpenConfig is really an ecosystem now. It wasn't just that you can go and write these data models. You can go and write these APIs, these RPC definitions, and make those available, and that's sufficient. You need to make them usable to the users that are going to consume them. And that's the software developers that are actually building these systems. And so we built a bunch of additional things that are actually where a lot of the effort of the project has gone, around code generation from those data models, around making those RPCs more usable, in why GNMI is an example for making GNMI more usable. We then started to think, well, we actually need to test these things as well. So we built test frameworks in Ondatra. And then we started to think, well, we need to simplify and improve the way that we can test those things through K&E, which is a Kubernetes-based testing, which Marcus Hines and I presented about a few nanos ago. And then further to that, we said, well, we also need some way to be able to test the compliance against these specifications. And so we started working on open source testing. And that's what this feature profiles approach was. So we overall built a large ecosystem of things that I would argue today makes OpenConfig the de facto standard for device layer abstraction in this stack. There isn't really another project or another set of interfaces that are available with the same API and the same ecosystem around them. But of course, it's not perfect for everybody. And this is a necessary thing in two dimensions, I would say. One is about what is represented, and then the second is in the coverage. And the first is more fundamental. So when we start to think about an abstraction, we said here that we wanted to be able to have things like portability. We wanted to be able to express things not in terms of every one of the nerd knobs that's exposed by every vendor implementation, but rather more a layer that could be portable across implementations. And to do that, then we needed to think about how to abstract ourselves from those things. So we necessarily didn't include every single knob of every single implementation. And there's a kind of philosophical thing here whereby we're saying, to be able to have this portability, we're going to have to ignore some of the very specific knobs that you might be able to change. And if you don't do that in an abstraction, then you end up with a very leaky abstraction. Essentially, you expose implementation details of a lower layer up the stack. And that would start to harm a lot of the advantages that I mentioned about having abstractions. So necessarily, we've made this choice, and it's encompassed in this idea of vendor neutrality, where we're looking not to expose every single implementation knob. And really, this still gives room for differentiation. You differentiate not based on the config that goes in. You differentiate based on the quality of the implementation that's there. The second set of concerns, well, OpenConfig doesn't necessarily cover everything that I use. And that is probably true. The focus of OpenConfig has been really around operational use cases. So we really took this approach and said, you can't really understand what the right abstraction to have is unless you understand what you're actually trying to do. And what does that mean? It means you need to have deployed it and had an idea about what the things that were important and the things that weren't important were. So really, there are gaps in OpenConfig because we want to get this abstraction right. And one could come and fix those gaps by being an operator or having some vision about how that deployment can happen and expanding the set of APIs today. But it's certainly not complete, and that's for these reasons. But it's not necessarily a novel concept to introduce these machine-to-machine abstractions. If we think about network protocols, what do we have there? Well, we have something where we don't expose all the implementation details, but we have a known input, maybe it's a BGP AFI-SAFI, which implies some level of behavior on a device. Maybe it's route selection or what's installed in the forwarding plane. And then we have some outputs maybe for advertising routes. So those things are essentially the same concept as we're proposing here, but just in the management plane. And so it's not really a unique idea here that we're saying, hey, let's have these machine-to-machine interfaces. We're really extending this idea of network protocols and just making them applicable to the management plane rather than the control plane. So there's a lot of background on the sort of picture of network management that I think we're working towards, as well as what OpenConfig is. What have we actually learned? What are the lessons that we can distill out of that? So this is the first one. And it's actually one that I think it's taken us way too long to learn in the networking industry. We haven't taken and embraced this idea that we should separate the data that's being carried in something from the transport that it uses. And historically, there were reasons for that. But let's just think about, say, OSPF and BGP. These are two things that propagate routing information. They propagate some different data, yes. But right down to the wire, they have different encodings. And so that means that every time we introduce a new API like this, we would need to go and learn a new encoding. We need to learn a new way that information is put on the wire, not just what the data is. And so this really hurts us in terms of the amount of knowledge that we have to have. And we haven't got any better about this. I picked a couple of very historical examples, but if you look at something like BMP, BMP is the BGP monitoring protocol. To be able to carry BGP PDUs from a device to some management system, I have a specific encoding. And if I want to come along and say, well, what about IGP PDUs? Well, then there's no way to extend that protocol in that way to be able to carry this data. So when we were thinking about the APIs that we designed in OpenConfig, we said we should make this separation very clear. And when we were designing GNMI, we actually designed it to be agnostic to the kind of data that it carries. Yes, we thought the target here is to carry OpenConfig model configuration data or telemetry, but it will work with vendor native models in the same way. It'll work with vendor CLI in a similar way. And it'll even work with binary encoded data that the protocol knows nothing about. So it's very easy to extend the protocol to carry new types of data without having to have different implementations and different understandings of how it works. And that's really because we thought about the primitives that we had. We have three simple primitives. We have get, set, and subscribe. And those give us very clear ways to be able to interact with a generic set of data underneath. There's some other advantages of adopting gRPC like we did in this case, insofar as we didn't have to worry about exactly how the data was going to be put on the wire to be performant. We could rather concentrate on the networking specific problem that we had about interacting with network devices. And I would say that you don't need to understand exactly how gRPC uses HTTP2 and how the streams in it are set up to be able to operate a network that involves these technologies. We've managed to extract some of that details away from the network developer and keep it within those folks that are building those transport protocols. Yes, you might need to understand something about TCP performance if you're debugging a throughput issue, but you probably don't really need to know very much about gRPC itself, if anything. And so this is a case where we managed to improve our velocity. We managed to improve the testing coverage that we get by reusing something from somewhere else. And we can extend that, not just thinking about GNMI and about the transport protocol and the data that's in it. We can also think about, well, what's the abstraction that we actually build in the system? And again, I don't think we've learned this lesson particularly. If you look at things like BGP segment routing TE policies, or if you look at PSEP, these are things, abstractions that worked with that are very specific to one's particular use case. If we decide to change the type of policy that we're expressing in these APIs, well, then we actually need to go and redesign the encoding. We probably need to redesign the API. And that in and of itself causes us to have more duplication of things. It causes us to have more things to test. It negatively impacts our velocity to be able to implement things. And so really, I argue that we need to think about these abstractions as being general purpose abstractions. We need to look and say, well, what are the fundamental things that we're dealing with in terms of on the networking device, in terms of from a networking perspective? And how do we build the abstractions around those things? And an example I would give here is when we built gRibbie, we thought specifically about, well, we want to inject something that's to do with traffic engineering. We want to inject some form of routes. But at the end of the day, all kinds of routes probably boil down to IPv4, IPv6, or the MPLS LFIP. Maybe we have some policy tables, but there's not very many fundamentals that we need to interact with. So by designing an API that was really around this idea of the primitives that are exposed by the network device, rather than a specific use case, it gives us the flexibility to reuse it across different implementations. Now we need to exercise a little bit of caution here, because if we applied this lesson and we tried to say, hey, let's go and build one abstraction to do everything, or one set of APIs to do everything, then building one thing to do everything often causes more complexity. So what I think the lesson here is that we take these abstractions and make them as general as possible. So that, but where there are differences, fundamental differences, we recognize those, identify them, and build alternate solutions. An example here is when we were thinking about the deployment of security policies onto network devices rather than configuration. We identified that there were just different primitives, different end users that needed to be involved. And so it was not worth trying to create the abstraction, the API, in a way that tried to encapsulate all those differences. It was better to have separation. But I would argue that where we've built general purpose things like GNMI, like gRibbie, these have built better sets of APIs devices where we're not going to go and build things in multiple contexts. So that leads me to thinking about, well, where do we need to do things that are networking specific? Generally, we have gone and taken things and said, well, here's a problem space that we're going to work on. And we've gone and defined a new networking specific technology. Maybe we've defined a new monitoring protocol. Maybe we've defined a new interface to a device. But we don't have to do that. And we should observe that there's orders of magnitude more developers that are working on non-networking problems than are working on networking problems. And equally, there's a lot of similarities between distributed systems where there are different components that need to communicate with one another and the problem of how we build our networks. So there's really an opportunity here for us to look elsewhere and see whether there's cases that we can adopt other technologies from other domains of computer science. And I would say here a good reason to do this is to just because of the amount of investment that went into building the ecosystem around things. If we look at the OpenConfig slide together, there are a bunch of things that we had to build that weren't really networking specific. And if you think about, say, netconf, for example, and then compare it to gRPC, well, there's not that many netconf clients out there. They're all developed clearly within the networking space. There's many different implementations of gRPC clients. And so just picking up a technology elsewhere lets us go and take something from another domain and not have to invest in building all of the fundamentals ourselves. And really, I would say that the biggest example I have of this is Yang. For those of you that are not familiar with it, Yang is a data modeling language. It lets you express a data schema in terms of nodes and the leaves that it has and their data types. And Yang, it was something where there were alternatives in the industry. If you look at, say, Thrift or Protobuf, these both do the same things. Now, Yang gives you some things extra on top of that. Maybe it gives you some better ways to be able to do data restriction because this is going to be an IP address. Maybe it gives you some ways to be able to interrelate between two nodes in a tree and explain some constraints there. For example, you shouldn't be able to configure ISS on this interface that doesn't exist. But those are relatively small wins when compared to the cost of adopting Yang. in terms of the work that we had to go in to build code generation from scratch, to build the runtime libraries around it, to even build the specification and own that specification going forward. So there's a lot of cost here to the Yang modeling language. And I'd argue we didn't get anywhere close to the return on investment that we should for putting in, building the ecosystem around it. Now, that being said, we did need to move from unstructured text, CLI text, being provided between network devices and the management system to some form of structured data. So it was a step in the right direction. But I argue we could have done a lot better by moving more quickly, by adopting technologies from elsewhere that weren't networking specific. So thinking about these abstractions between network devices and between layers of our system, another lesson that I think we can take is that the way that we should think about those abstractions and those APIs is as contracts. If we think about what they do, they basically tell us some input, some behavior that the system should do based on that input, and potentially some output. And we get a point at which, for each of those things, if we write these specifications correctly, these abstractions correctly, we can test against them. We can say, is this contract actually adhered to by this component? And doing that gives us a few steps forward that I think we can make. If you imagine how you write a specification for a vendor network device today, you probably have a bunch of RFCs and maybe sections that they need to implement. And you list those as this is what should be implemented by this network device. The problem with this is it tells you nothing about what needs to be configurable. It tells you nothing about what telemetry you need from the system to tell whether it's running. And maybe it doesn't even really clearly tell you what the behavior should be. It's down to interpretation of prose. And so rather than thinking about those kind of contracts, if we think about the software interfaces that we're building as the way that we have contract enforcement points between different systems, it gives us a really clear way to be able to explain requirements, to check compliance against them, and to evolve those components separately. And some of these interfaces might need to be stronger contracts than others. If there's a contract between two systems within your own stack, maybe it doesn't need to be a super strong contract, but it probably still needs to exist such that you can evolve those things separately. In the case of OpenConfig, I think we learned this lesson really clearly, because it's not just that there's multiple client layers that are going to come along in terms of different operators or different ways to interact with devices that are being built. But also, there's multiple implementations at the device layer. There's not just one where we're trying to describe its behavior. We're trying to generically describe across multiple vendors how this should work. And so having this as a contract enforcement point really gives us a way to be able to improve that testing, improve that velocity, catch regressions earlier on, because we've really described at that single layer what the device should do and how we want it to work. And that lets us evolve this network system more completely. Now you'll note that to be able to do this, and be able to think about OpenConfig in this way and think about the abstractions in the system in this way, we can't just think about a single layer. We can't just think about this as like, oh, this is the interface to a device. We need to think about this in terms of an overall system architecture. We started out with this idea of this layered system with separation of concerns. And we started out by thinking about how to break that down. And so I would argue that we have to think not just about scripting and the tools that we're using, but also the system architecture that they're going to fit into. And that isn't just a single operator thing. There might be differences of deployment, but I would argue there's really quite a clear set of fundamentals that we could go and define. The device layer is probably the most obvious because we often use equipment supplied by other companies. But having that layered system gives us a way to be able to reason about what the right things to build as the community are, how to make them reusable across the case, but also to reason about what their functionality needs to be. We have to look at what we want in terms of the overall system to be able to define the functionality of each layer. So you can probably observe that I'm not really arguing for anything particularly different to other domains of computer science here. I'm saying that we should have interactions that are in terms of abstractions between different systems. And this quote is often attributed to Butler-Lamson. And it's actually all problems in computer science can be solved with another layer of indirection. I'm going to use abstraction as a synonym here. But really, what I'm arguing for is taking that approach of building these layered systems with separation of concerns, with clear APIs between them, like you might have in a microservices architecture in any other application, and applying them to networking and learning the lessons from that. And as I said, it wasn't that we just sat down in a room and decided that these are the lessons, that this is the approach. At Google, we've learned this iteratively. we have built our systems multiple times. We've iterated on what's there. And I think we've distilled down to a couple of examples that I can give where applying these lessons has given us a better way to be able to build the systems that we're thinking about. And the first of these is this approach of building a layered management system. If I think about this system that we've built, we applied these layers and separated concerns out. So for example, we have this top layer that we think of in terms of network actions. These are things like adding capacity to a device, adding a new service to a device. All these things can be encapsulated along with their logic at one layer. And you have the process that's required there, but also the health checks, the safety checks that are needed at that layer. What we do is then take those actions and distill them down into an abstract set of network operations. So this is like adding an abstract link, adding a logical link between two nodes, adding a new node to a graph. And the topology and service abstraction layer handles that. And this is where we get the chance to enforce things like what valid topologies are. We get to enforce things like you can't remove that link from operation because that will isolate this location. And that layer then can be concerned with that. And we've talked a bit about this in terms of, we wrote a paper and published it on MALT, which is our topology modeling language that we use for this layer. That layer then expresses in an abstract way, not knowing about how exactly it's going to be implemented, to a device abstraction layer that then itself can go and determine what the set of changes that are needed to network devices are, whether that be in terms of OpenConfig or not. And so at that point, we don't care now what the vendor of the device is. We don't care necessarily what the way that we push the configuration to the device. We have a layer that's able to deal with that and is independently testable. And this architecture gives us a way to be able to work across multiple different types of network device. We have this in production for a number of years, and it's across both IP and switching, optical, and even in radio that we have, such as wireless. And we don't just have this stack in the write direction, we also have it in the read direction. So where we're taking things from the device and providing abstractions further up the stack so that each client layer can figure out what it cares about and translate it into a way that's meaningful for its clients. We've also taken this beyond the management plane and thought about it in terms of how we might build other applications. And this goes to the reusability point and the point about building general abstractions. Here we've built abstractions that let us extract state from the network and push changes to it. And if we think about what a control plane system does, essentially it uses those two things together to make changes to the network. And so we can take the things that we've built primarily for the management plane and extend them and build this kind of hybrid SDN architecture, which is a patch to the original SDN architecture with control plane, data plane separation. Rather gives us a way to be able to have some control plane that can run on the networking device, ways to interact with the applications that are there, and then to be able to build things that need to be in these off-device systems, in those systems, and things that need to be on the device in the way that we may have done traditionally or the way that's most efficient to do today. And so this is another approach that we've taken to building these kind of systems, reusing the set of APIs and abstractions that I've talked about. Now, where I've spent a lot of my time in this journey is not just being on the software and the technology and the network development. It's actually been on the cultural side. And in this case, there's a big disconnect between network engineering and traditional software engineering. We need both sets of folks. We need the folks that run networks because they know all the details of how to run networks and the complexities of doing so. But we also need the knowledge that comes from the software engineering area. You know, how to build maintainable systems, how to design these abstractions in reusable ways. And so one of the big challenges has been trying to unite those two tribes, having to being able to translate between them. And I would argue this is one of the biggest areas that we need to work. We need to work to make sure that we as network engineers and we as software engineers are appreciating what the other set of folks do, and learning their lessons as quickly as possible, not necessarily having to repeat the mistakes that we may have made. And so this involves us needing to think about how to evolve network engineering, how we teach people network engineering, and what we teach them in that context. So I'll leave you with the summary of these lessons. My core premise here is network automation is a systems problem. It's not a scripting problem. It's not a software engineering problem. It's not a tooling problem. It's a systems problem. And there may be all of those things within it, but we need to think about how we're going to build the network and automate the network in terms of the overall network system. And we've definitely made some strides forward in the last decade. The set of tools that are out there for us to adopt is significantly larger than it was before. There's many different approaches. We're not just constrained that you must use the CLI and expect. But we should really strive, as we continue as an industry to go down this route, to learn from other domains. We should really strive to see how we can pick up their lessons, how we can adopt their technologies if they're suitable for our deployments. And then we need to continue to evolve network engineering to include this kind of systems thinking, to include the way that we think about building the overall system. Network engineering is no longer just connecting devices together and OSS is somebody else's problem. It really has to be a combined system that works as we need it to do so. So thanks very much indeed. I'm very happy for any questions or comments.
Oh, hello. Thank you. Very nice presentation. I'd like to, Maria, developer of BERT, CZNIC. Thank you for having the opportunity to have the first comment and question. The situations where we are using abstraction and automation is typically in modeling various and different networks, and typically we hit lots of bugs and problems on the way. The problem which I am seeing with adding more and more layers is that the more layers you add, when some bug appears, you have to dig through all the layers, and with adding the reliability, you are losing the manpower, the people power, sorry. You are losing the information in people's heads, how to actually dig through it, because the actual problems with those happen once, twice a year, and then there is actually nobody who knows how this is working in completeness. And we are slowly but surely getting to a situation which we have with clothing or with other like plastic things, when we, instead of repairing things, we are going to put the server out of the rack, reinstall it, and put it there once again. And the question is, do we want to go there, or are we going to hit the same problem as the clothing industry and the plastic things have gotten into? And for example, in the EU, there is now the right to repair going on. So where do you think it is going?
I think that there is definitely a change where we are saying it's not possible, or we're saying there are individuals that don't, there's no individual that necessarily knows how all these things work together. I would say we're already there. We've already been there for some time. If you ask most folks, exactly how did the internals of this BGP implementation work? That was already abstracted. So there's already a need to go to TAC or to go to somewhere else. As we introduce more layers, we probably don't want infinite layers. But I think having separation of concerns makes it clearer what the correctness of those layers should be. And so it gives us ways to be able to test against them and say, are they doing the correct thing? It gives us monitoring points as well to be able to keep monitoring and saying, is this doing the right thing? Now, that's not to say it's going to be bug-free. It's software. It's going to have bugs. And so I think there are cases here then, to your second point, about we have to think about how the operational practices potentially work in ways that make that scalable. So the example of we reinstall the server, maybe that is the most scalable way to solve some of these problems that helps us address this. But I would say networking is no different here, right? Like there's many systems. I do not know the internals of how my OS kernel works, but I still have a laptop. And I still run and manage to work with it. So I think we're inevitably going to be in that position where there is not a single person that knows. And we have to figure out what the tooling, the monitoring, and the testing we need to have to make that maintainable, that system maintainable is. And that's actually my argument for layers, is because if we go and build one layer, I don't even know how to build the one layer. I don't know how to test the one layer without actually going and building my network and going and doing those processes again. So I think it's definitely a risk. And this is I would say, the systems architecture problem. It's figuring out what the right set of layers are, how we build that together. And it's different to a traditional network architecture position, right? It's thinking about how you build software systems, not how you build reliable networks. So that's my argument for more of it. So I don't disagree with the point, but I think it's inevitable that we're going to land there. I hope I'm not throwing my network away when it breaks, though. That seems like a problem.
Thank you.
Hello, Brandon Bennett with Roblox. Thank you very much for the talk. I think it was wonderful. However, after dealing with OpenConfig and dealing with GNMI and dealing with all these different components, I feel that what you presented was a very idealized view of the world. There was a slide where OpenConfig was the de facto standard. And after developing against GNMI and looking at OpenConfig for config generation, we still had to build the other interfaces as well to complete the ecosystem. And it makes me wonder, was it worth it? If I'm still building HTTP REST interfaces to eAPI just to get this one command, or building even CLI scraping still. So it's been 10 years. I guess, why has it taken so long? And how can we speed this up and actually get true adoption?
And I think that's actually the way that some of the lessons I would like us to learn are exactly about this, right? If you think about the problem of OpenConfig adoption, well, you didn't care about Yang, right? You probably didn't really, it didn't matter to you if we'd written OpenConfig in protobuf. Actually, it probably would have been better for you, because if you weren't, you're not using Go or Python, you're a little bit out of luck. And I say that as the person that wrote 2 code generation pipelines for it. I certainly didn't understand that when we started down this pattern, I was going to spend multiple years of my life writing code around the things, not concentrating on the problem of what's the right modeling and what's the right, getting that implemented. And so I think here, if we'd been able, if I think about the collective brain power that's gone in over these 10 years, if we'd been able to say, these people are interested in networking, they know about networking, I want to apply their knowledge to the networking specific problems and not the overall problem space, I think we would have gone a lot quicker. And so everything you said is correct, right? There's not 100%, I'm not going to say like, hey, there's 100% nirvana here. Getting to it has been extremely long. It's been a commercial problem as well as a technical problem. But if we just take the technical problems, I think we just solved the wrong problem for a bunch of time. And I think that standards organizations are not helping us with this. I think like, if you look at the fact that we invented a new modeling language, and we didn't just look at what was out there, it's just the wrong thing to have done. And so, yep, I think the way that we make quicker progress going forward is we think about the systems problem, we figure out what the bits we need to solve are as networking folks, and then we go solve those bits. And we say, oh, great, we can steal something from somewhere else, let's do it. I'm fundamentally a very lazy engineer. If I can avoid writing code, I'm going to do it. And so even if it's not 100% perfect, we should do it. And I think that's what some of the traps we've fallen into, is trying to get something that's 100% perfect for networking rather than something that's 80, 90% good enough.
Thank you.
Mahesh Jaitanandani, Arca Systems, talking about stealing ideas from other organizations. When you flashed your stack, I was kind of reminded of MEF and their LSO reference architecture. They kind of touch upon the same layered approach. And one piece of that network, if I want to say, that networks don't necessarily operate in isolation. They do have partner domains that they have to work with. They have customers that they have to deal with. And I thought in your diagram, when you talked about layered approach, you could also horizontally expand to what it would take to interact with a partner organization or with a customer.
I think that's a fair comment. I think the beauty of using abstractions, like with protocols, right, is that we only have to agree with them at the borders. So, I also agree, hey, I just drew a few layers up. I can go and look at a lot of different computer science systems, a lot of different systems, and say, oh, there's a layer that does that, there's a layer that does that, there's a layer that does that, that interacts with some hardware. It's pretty much the fundamental of fundamental architecture. So there's nothing new here. I'm just really actually trying to encourage us to think about networking as a computer science problem in a bit of a different way than I think we're going as an industry right now.
Agree.
And I think on the interchange point, I agree with you. There are definitely places where that is required. I'm encouraged to see there being more discussion about that. Great. Thank you very much indeed.